Good morning. So let's go ahead. Start off by taking a look at the schedule for the next couple weeks because we're almost done. Hopefully everyone had a good break. Maybe you got to see some family. Maybe not this year. It's been a little weird. But hopefully you at least got to enjoy the break. So where was it? Okay. So as far as the rest of the semesters go, this week we're going to do solutions, and we may kind of pack acids and bases into this week as well if we've got time. Next week is acids and bases, and then we should have some time for our final review. This being a review for the entire semester, the entire final exam. Your fourth test will be on Sunday, Monday of the week before finals. And then your final exam will be on Thursday from the 17th to the 18th. And if there happen to be any late lab submissions, I can give you some really, really low grades on some of those. But if you want to submit them, you can get them to me by the 13th, which is next Sunday. So yeah, so we're almost there. We did pretty good last week as far as getting into solutions. So we left off, we had talked about the different types of ways to represent concentration. So we had, mass percent. And then we also had molarity. So mass percent is comparing grams to grams. Molarity is going to be moles over liters, which is the most useful one that we have. And then I want to do one more that isn't in the slides, but is still useful, and it's in your text. And that's mass volume percent. Okay, so the final one we have is mass. I mean, there's other ways too of explaining these things. There's molality, there's different things, but for the sake of this class, I also want to do mass volume percent. And it doesn't really make a whole lot of sense because how can you compare mass and volume? They're two different units and still be a percentage. It's kind of funky, but just go with it. So this is going to be mass of the solute. Put it in grams over volume of solution. And this is in milliliters, okay? That's a little bit different from what, and then we times this by 100. But the milliliter component of this is a little bit different than what we've seen, for instance, with molarity, which is per liters. So just make sure you're getting that into milliliters. So I'll give you a problem of what is the mass volume percent of 16 moles of Al2S3 dissolved in 18.75 liters of solution. Okay, so what is the mass volume percent of 16 moles of Al2S3 dissolved in 18.75 liters of solution? So I will give you about 5 minutes, 3 to 5 minutes to work on that. Look here to what you need your units in. Notice what your units are given to you. All right, so when we're trying to figure out mass volume percent, we need to have the mass of the solute in grams, and we're given kilograms, or rather we're given moles here. So I need to convert that. So 16 moles of Al2S3. We can switch out for every 1 mole of Al2S3. We have a molar mass. One second. So we've got 150.158 grams of Al2S3. And so we end up with 2,402, really, 3. Oh, and then, sorry, and let's get the units in 3 grams, yeah, of Al2S3. So then I need to convert my liters into milliliters. So really the easiest way to do that is just to move the decimal over 1, 2, 3 spots, fill it in with a 0. So this equation is going to be 2403 divided by this 18750, and then we want to multiply it by 100. And we end up with, there's only 2 sig figs in this thing here, so we end up with 13%. So the mass volume percent would be 13. Any questions on that? Anything not matching up? Excuse me. All right. Let's move on. Okay, so sometimes we want to report what the ion concentration is of a material in solution, because when we put something into solution, it dissolves, and if it's a ionic compound, it'll break apart into its ions. If it's a molecular compound, it will break apart just into the molecules. So the reported concentrations of solutions whenever it's containing a molecular compound usually reflects the concentration of the solute as it actually exists. So for instance, if I have a 1 molar glucose solution, it's this thing here, because this is molecular, and we know it's molecular because it's all nonmetals. If it's 1 molar, that means I have 1 mole of this glucose dissolved in every 1 liter of solution. For ionic compounds, the reported concentration of the solution containing ionic compound reflects the concentration of the solute before it is dissolved in solution. So if we look here, this says a 1 molar CaCl2 solution would contain 1 mole of calcium, because look at, I'm getting 1 calcium in every 1 of these formula units. But I would actually be getting 2 moles of chlorine, because I get 2 chlorines for every 1 of these ionic formula units. So the concentration of the individual ions present in solution containing an ionic compound can be approximated from its overall concentration. So if I know its overall concentration, I can figure out the individual ions, because it's directly related to however many you get per formula unit. So let's look at this one here. It says determine the molar concentrations of the sodium and the phosphate if we have 1.50 molar Na3PO4 solution. So I know that I have 1.50 molar Na3PO4. If I want to figure out the concentration of the Na plus, well, I need to figure out how many NAs do I get for every one of these formula units. So for every one of these things, I'm actually going to get 3 sodiums. So if I have 1.5 molar, I'm going to need to multiply that by 3 because I get 3 every time it breaks apart. And we end up with a 4.5 molar concentration for the Na plus ion. So it's a pretty easy calculation. You just multiply by how many you have. Now for the PO4, this thing, how many of those do I get? I only get 1. So I would just take whatever my initial concentration is, 1.50 molar, and we multiply it by 1, or it'll be equivalent. 1.50 molar PO4, 3 minus. So moving to the next concept here, talking about solution dilution. So usually in a lab setting, in the back of the lab or somewhere where you guys wouldn't have access to, there's a stock room where we have what are known as stock solutions. And these are highly concentrated solutions. And it doesn't make sense to have, like, say, for instance, we're talking about hydrochloric acid. It doesn't make sense to have a 1 molar hydrochloric acid and order a 2 molar hydrochloric and order a 3 molar and a 4 molar and a 5 molar, because it would take up so much space in your stock room. So instead, what we will do is we'll get a highly concentrated hydrochloric acid, let's say like a 12 molar hydrochloric acid. And then anytime I want to run a lab where I need a 4 molar hydrochloric acid, I don't keep the 4 molar on hand. I'll just dilute the 12 molar to a 4 molar concentration and make as much as I need as needed. And I can do the same for all sorts of funky concentrations. Let's say we needed a concentration that was like 1.33 molar. We could also pull that from just the 12 molar. So it's a way of keeping your stock room sane, right? Just having these higher concentrations. So how does that, or why does that apply to the lecture side of this? Well, because we can actually calculate how much of that 12 molar hydrochloric acid we would need in order to make, let's say, a 3 molar hydrochloric acid solution. This simple equation only applies to solution dilution. So you don't want to use this with solution stoichiometry, which we will talk about a little bit later. But this is really only referring to situations where it says, hey, I've got a concentration of this and I want to dilute it to this. How much do I need? And so the equation is right here, and it is M1 V1 equals M2 V2, or the initial molarity times the initial volume will equal the final molarity times the final volume. Sometimes you may see this equation written like this: C1 V1 equals C2 V2. This is just saying the initial concentration is equal times the initial volume is equal to the final concentration times the final volume. So in this top one, you could plug in something like mass volume percent or mass percent. This final one is only referring to molarity, but they're pretty much the same thing. So as far as the concentrations are concerned, as long as they're in the same units, you can use whatever concentration. Same thing with volume, as long as they're in the same units. So you could technically use milliliters here. You don't have to convert to liters or anything like that. So it's a real simple equation. Oh yeah, I got a case of the Mondays. The case of the Mondays after a break. Always tough. So why does this equation work? The equation works because the molarity multiplied by the volume would give you the number of moles. And we're technically not changing the number of moles when we're diluting something. We're just making it more diluted. This is not for solution stoichiometry. So don't use it if there's a balanced equation involved. One thing to note, when diluting acids, always add acid to water. Never add water to concentrated acid. So acid to water, safe as an otter. All right, so if we look at this one here, this says, prepare 5 liters of a 1.5 molar KCl solution from a 12 molar stock solution. So when looking at this equation, one thing you may want to write down is that the ones or the starting, this is your concentrated stuff. All right, and your twos over here, this is your diluted stuff. So whenever we're talking about diluting something, we're going to put it in the 2 part. The concentrated, we'll put it in the 1. So this says prepare a 5 liter of a 1.5 molar KCl solution. So both of these are referring to your twos, right? Or your diluted stuff. You want 5 liters of a 1.5 molar solution. In the back stock room, you only have a 12 molar solution. So this is asking you, well, how much of that 12 molar do you need in order to dilute it down to 5 liters and get this exact concentration? Well, using our equation, we want to solve for the initial volume because I want to know how much of that 12 molar solution do I need to measure out? Like, do I need to measure out 5 liters of it? Probably not. Do I need to measure out 1 liter? What is that number? So we isolate for V1. So V1 will equal M2 V2 over M1. And then we just go ahead and plug in our information. So the twos are our lower concentration things. So the 1.5 molarity times the 5 liters divided by our more concentrated M1, so the 12. What we find is that we need 0.625 liters of this highly concentrated solution. We would take that, dilute it down to 5 liters or dilute it up to 5 liters, and then it would give us that magic concentration of 1.50. Pretty basic. We'll pause on solution stoichiometry for a minute. Let's do a couple of these solution dilutions. No, I'm just gonna make one up for y'all. Okay, so what is the final concentration of a 12 molar HCl solution diluted from 1.5 liters to 8.6 liters. I'll give you 2 minutes for that. All right, so looking at this problem, it's talking about diluting a material. So we're just talking about hydrochloric acid and we're diluting it, so we don't need to do anything more complicated than M1V1 equals M2V2. So my M1, and this is my initial concentration, which is 12 molar. Specifically, it's HCl. My V1, well, it says I started with 1.5 liters. My M2, or my final concentration, well, that's what we're trying to find. In real life, you usually don't just like make random solutions and not know the concentrations. Usually you know the concentration and you try and find the volume, but just for the sake of playing around with the equation. And then your final volume we said is 8.6 liters. So we want to figure out our M2, this guy right here. So that means it will be equal to M1 V1 over V2, because if it's multiplying on this side, it needs to divide on the other side. We plug our information in. My initial concentration is the 12 molar. My initial volume is the 1.5 liter. And my final volume is this 8.6 liter. What we'll see is the liter units cancel and we'll be left with units of molarity, which is a concentration, which is what we would want when solving for concentration. So we take the 12 times the 1.5 and then we divide it by the 8.6. And we come up with our M2, our final concentration. Sig fig wise, we'll go with 2 sig figs. So it's 2.1 molar. So 2.1 molar HCl solution. Any questions on solution dilution? Okay, so the next thing that we're going to talk about is solution stoichiometry, which is a little bit more involved than solution dilution. So in reactions involving aqueous reactant and products, meaning that we have a reaction and it's happening in a water solution, it's often much more convenient to specify the amount of the reactants and products in terms of their volume and concentration. So instead of giving grams, like, hey, I have 55 grams of hydrochloric acid, I would say, hey, I've got 100 milliliters of a 12 molar HCl solution. Now, if we have volume and concentration, we can calculate the number of moles, right? Because molarity equals moles per liter. So if we know molarity and we know liters, we've got moles. Anytime we know moles, we can do stoichiometry if we have a balanced equation. So this is going to be sort of the general flow chart for a lot of these problems. Volume of A goes into moles of A goes into moles of B, and moles of B back into volume B. And I'm going to add this to our other stoichiometry flow chart over here. I'm going to draw it out for you. So if you're like, oh man, stoichiometry, what was going on there? That was when we were going from grams into moles, specifically grams of A, into moles of A, into moles of B, into grams of B. And let's talk about how we got there. So this grams of A to moles of A, this was molar mass of A, right? Molar mass of A. This was molar mass of B. And how did we get from moles of A into moles of B? This was that magic step where we had our coefficients from the balanced equation. All right. Now I can add some limbs here. One limb that I can add here, make that narrow. Just make it a line, is volume of A. And then I can stick, no, don't want to put it there. Stick it here, volume of B. How do I go from volume A into moles of A? I would have to use the molarity, specifically the molarity of A, okay? Here it would be the molarity of B. So now I've got sort of a new way to move through this flow chart. It disregards grams. We take our volume A, we use the molarity of A to get to moles of A. Then we can use the coefficients of the equation to get to moles of B. And then we can use the molarity of B to get us back to volume of B. I'm going to add another limb down here and down here. And I'm going to put molarity of A. So I could technically have the molarity of A instead of the volume of A and get into moles of A by using the volume of A. And I could end up with molarity of B. And I can do that by the volume of B. Right? Because if I know moles of B, I take the moles divided by the volume and it gives me the molarity. The nice thing about this sort of master chart is that you can take different paths. So I could start with a volume A and end up with a molarity of B by going down, over, down. Or I could start with molarity of A and get to volume of B by going up, over, up. Or I could get molarity of A and go into grams of B, right, by going this way. So it all sort of ties in together. But we're going to look really at this top part here for right now, just to practice it. So how do you know that you need to be following this flow chart or even be doing stoichiometry? A couple indicators. You're going to be dealing with A and B, which will be two different substances. So it'll be talking about, say, like a hydrochloric acid and like a sodium hydroxide, as opposed to a solution dilution where it's talking about the same material just being diluted down. Also, if there's a balanced chemical equation written there, you probably need to use it. Okay, so let's look at this problem here. It says, how much of a 0.125 molar NaOH solution do we need to completely neutralize a 0.225 liter of a 0.175 molar H2SO4 solution? And outside of this telling you it's solution stoichiometry, I know it's solution stoichiometry a couple different reasons. There's a balanced equation. And I'm going to sort of transfer this to my whiteboard because I don't fully like how they describe how to do this. I want to give you a little bit more detail. So one thing that indicates that this is solution stoichiometry outside of it saying it is that we have a balanced equation. So we have this H2SO4, and this is an aqueous thing. It's combining with two NaOHs, also aqueous. And what I can see here, you know, if I want to talk about this reaction a little bit, is this is an acid combining with a base. So we should end up with a salt and water. And what do we end up getting? Na2SO4, which is our salt, aqueous, plus 2H2O. There's our water. Okay. All right, so we've got information about NaOH and H2SO4. I'm just going to write it out here. So how much 0.125 molar NaOH solution do we need to neutralize 5 liters of 0.175 0.75 molar H2SO4 solution. All right, so when looking at this problem, it's saying how much, and when they say how much, they're talking about liters. Okay, how much, and this is referring to liters of this concentrated solution do we need to neutralize a certain amount of this H2SO4? So right off the bat, I'm going to be following this part of my flow chart for my solution stoichiometry for this specific question on solution stoichiometry. So we're going from here down to here, over, and then back up. So what I always like to do with solution stoichiometry is figure out first what is compound A and what is compound B, okay? So compound A is whatever you're gonna have more information on or two pieces of information on. So compound A for me in this problem is going to be the H2SO4. Why? Because I know both its volume and its molarity. NaOH, I only know its molarity. So compound A is H2SO4, and I'm gonna write that out. My molarity is equal to 0.175 big M of H2SO4. Now with solution stoichiometry, we're doing dimensional analysis. So molarity written like this is not very useful. So I'm gonna change this into moles per liter. Remember, writing it like this, I can also write it like this, 0.175 moles of H2SO4 over every 1 liter of solution. So those two things tell me the same thing. This I like much better for solution stoichiometry. What else do I know about compound A? So we've written that out. I also know its volume, right? And in this case, its volume says 0.225 liters of solution. If for some reason this was in milliliters, convert it to liters, okay? So make sure volume is convert to liters. Why? Because molarity is in moles per liter, so milliliters won't be useful here. Now I need to put down what my information is for compound B. So compound B is whatever I have less information on. So NaOH, I only have one piece of information here, right? I know its concentration. So I know molarity is equal to, in this case, 0.125 big M of the NaOH. And again, I don't really like it written like this because I'm going to have to do some dimensional analysis. So I'm going to right off the bat convert this into mole per liter. So 0.125 moles of NaOH in every 1 liter of solution. And it's specifically 1 liter of the NaOH solution, right? This is the H2SO4 solution. I'm trying to find the volume. I don't know the volume. So now we set it up. And that flow chart from the very top up here tells us that in order to go from volume of A into moles of A, we need to use the molarity to convert. Then from moles of A into moles of B, we use the coefficients of the balanced equation, and then moles of B into volume of B, we use molarity of B. So let's start off right here. It says to begin with volume A. So where is my volume of A? So here's compound A, and here's the volume already written for me in liters. We have 0.225 liters of H2SO4 solution. Now, that first part of the flow chart said to use the molarity, so this is my molarity, as a way to convert from liters to moles. So looking at this, moles I'm going to put on top, liters I'm going to put on bottom, so that we can get into units of moles, H2SO4, and we can get rid of the liter. Right, so liters will now cancel. Now I'm in units of moles of compound A, or units of moles of my acid. Right? So we've done this first step. We need to go from moles of A into moles of B, and this is where we use the coefficients. So here's our balanced equation. Coefficients, well, for every 1 mole of the H2SO4, I will end up with 2 moles of the NaOH. So let's go ahead and put that into our dimensional analysis here. On the bottom, I'm going to put the 1 mole of H2SO4 because I want to get out of my initial compound, my compound A. I want to get into my compound B, or the NaOH. Well, we get 2 moles of NaOH. NaOH for every 1 mole of this H2SO4. So the moles of H2SO4 will cancel, and we're in moles of compound B, or the NaOH. So we've gone from here to here. We're now here. The last step is to get the volume of B. And the way I do that is I use the molarity of B. So if I know moles of B, well, I just need to take its molarity and arrange it in such a way that I end up with volume. So looking at this, moles are on the top here. So I'm going to want to have my moles on the bottom. So I'm actually going to want to flip-flop this relationship and put the mole part on the bottom. So 0.125 moles of NaOH will yield 1 liter of our solution. And look, the moles will cancel there. So now what we need to do is just plug all that messy stuff into our calculator. 0.225 times 0.175 times 2 divided by 0.125. We should end up with, I'm just going to do it a second time because I don't trust all my decimals too. Okay, so we get 0.63, and what are my final units? Liters of solution, specifically liters of NaOH solution, right? We're trying to find the volume of B. Isn't that fun? So make sure you have this sort of master flow chart available to you when you're working through your exam. Let's see. And so they sort of set it up the same way. They say, hey, you want to go from liters of the initial into moles of compound A, into moles of compound B, into volume of compound B. And they get the same answer as we do. We're gonna do a couple more practice problems with that though before we finish up. So I don't think this one has anything. Okay, yeah, let's do this. So let's look at this first one here. So we have a balanced equation. How much of a 0.20 molar H3PO4 solution is needed to react with 100 milliliters of a 0.10 molar NaOH solution. So we're going to break this down. The first thing I want you to do is write down the problem. And then I want you to tell me what compound A is, what compound B is, what your knowns are, what your unknown is, and then convert anything that's in molarities to moles per liter and any volumes that are in milliliters to liters. So let's start with just getting that set up. I am going to transfer this over to my other slides, whiteboard. Okay, so what we are going to do here, first step is just to, I wish I hadn't written it so close, but I did. What can you do? I'm gonna put it down here. So I need to have compound A and compound B. So compound A, remember, is whatever you have more information on. So I have two pieces of information about NaOH. So we're going to make that my compound A. NaOH. So what do I know about NaOH? Well, I know its molarity. Its molarity is 0.10 big M NaOH. I'm going to rewrite that as 0.10 moles of NaOH for every 1 liter of solution. What else do I know about compound A? I know its volume. So volume in this case is 100 milliliters. right off the bat. I don't like milliliters. I'm going to convert that to liters, which is going to give me 0.100 liters of my NaOH solution. The next thing I'm going to do is identify compound B. So compound B here is the other thing, whatever the other guy is. So in that case, it's this H3PO4. And this thing, I only know one piece of information. I know it's molarity, I know it's concentration, right? So molarity for this guy is 0.20 big M of H3PO4. And again, with solution stoichiometry, let's just get that into moles per liter. So it's the same thing as 0.20 moles. Not let me write. Over every 1 liter. This is specifically the H3PO4. I'm trying to figure out volume, okay? That's what I want. So we don't know what this is. So hopefully you're able to do that. You know your compound A, you know your compound B. Now we're gonna break again, and I want you to set up the stoichiometry to get from this stuff over to this piece of information. And just a reminder, we can look, everything's in my way. Here, we want to go from volume A, moles of B, into volume B. I'm going to give you all about 4 or 5 minutes to set that up, and then we will go over that. Please ask any questions if you're not sure about where this stuff here came from, how to pull that out of this. I want there to be clarity there. Because I feel like if you can get this set up here, the rest of it becomes much easier. If you don't have this laid out, what's compound A and what's compound B, where are you starting, where are you ending, the problems feel really, really complicated. Just another minute to finish up. All right, so when looking at our flow chart, we want to start with volume A, go into moles of A, then moles of A to moles of B, and then moles of B to volume B. So I start with my volume A, which is conveniently written for me right here. So we have 0.100 liters of NaOH. I'm going to convert this into moles using my molarity. And I can set it up just this way because the 1 liter of the solution will go on the bottom and the mole value will go on the top. 0 moles of NaOH. Liters cancel. Now we want to go from moles of compound A, so here's my compound A, into moles of compound B, or what we have less information on. So here to here, we use the coefficients. So it's a 3-to-1 relationship. 3 moles of NaOH will yield 1 mole of the H3PO4. So there goes my moles of A, and now I know my moles of B. Now the last thing is to get into volume. So if I know my moles, I can use my molarity to get into volume. Now here's moles, and moles is on top here. So again, I need to flip-flop these two guys. So I'll put the 0.20 moles of the H3PO4 on the bottom, and this will yield 1 liter of H3PO4. The moles will end up canceling. So now we plug this in. 0.100 times 0.10 divided by 3 divided by 0.2. End up with a value of 0.017 liters of the H3PO4. And if I was to write this as a, let's say the problem wanted it in milliliters, I could easily convert 1, 2, 3 back into 17 milliliters of the H3PO4. The problem may have wanted it in milliliters because they gave us the information in milliliters. Okay, either of those would work. Just make sure you're using your units correctly. Any questions on that from anybody? It can be kind of tricky, but I think if you can go step by step, it helps. Okay, so that is don't let me speak before. So we're not going to talk about boiling points or freezing points. So we'll skip over that last part of the chapter. We're not talking about osmosis either, or osmotic pressure. That's something that we'll expand upon in 151 or 130, depending on what chem you go in after this. So yeah, so that's the end of the chapter. So we'll end with solutions. If you have any questions, feel free to stay around. Lab 12, we're just not going to do it. We're just not going to do the solutions lab. Okay, so I will eradicate that from the grade book. Again, if you're unclear about anything, please stay around. Otherwise, enjoy the rest of your day. We're in a good place for the rest of the semester, so we'll start acids and bases on Thursday, and then hopefully have some time for review next week. Bye, guys. Do we get any credit for already doing the lab? I will, I'll take it into account. I'll take it into account at the very end of the semester. I'm sure your grade will be fine, but if you're right on the cusp, it'll maybe help. But yeah, all right. Gabriella, Suzanne, do you all, either of you have questions?
I did. Did you see the chat? Well, I can say it now. But...
Hold on 1 second. Let me, Suzanne, I'm going to put you in a waiting room. Okay. Oh, no, she already left us. Okay. Yeah, you can talk. So what's up?
So I've got some homework that's pretty late, and I was going to try to work on it, but I don't know if I'm going to get any credit. So I was going to see if I would get any credit if I turn.
Yeah, I'll give you some credit for it.
Okay.
So work on it. Yeah.
All right. Thank you.
Okay. Bye.
Bye.